This is Heat Transfer Lecture on Chapter 13. In this lecture, we're talking about radiation exchange between surfaces. We're still on enclosures with non-participating media, and this is sections 13.3.3 through 13.4. In this lecture, we want to start with talking about a special type of surface that we call reradiating surface. These are surfaces that are well insulated on one side to basically not allow conduction on the back side of the surface, and then their convection effects are also negligible. The top surface where you have radiation could also have convection effects. For example, you could have air on top of your surface. We're assuming that there is no convection as well, or it's very negligible. So basically there is no conduction on the back side of the surface, there's no convection on the top side, and if you do have steady state conditions, we are going to say that the heat that is coming to the surface, or irradiation incident on the surface, GR, is going to be equal to the radiosity of the surface. Now for surfaces like this, we basically say that no heat passes through the surface, which is QR is equal to 0 here. And if you were to actually write QR equal to 0 or see what that means, we would be able to say that in order for me to write the QR relation, I'll be able to pick the two nodes from my surface and my radiosity node. So I'll be able to say that EBR, we call it R because it's a re-radiating surface. It's just the name of the surface. And then JR divided by the resistance between them, epsilon R A R. If we set this equal to 0, that means that your EBR is going to be equal to JR, or in other words, your radiosity node is going to be equal to the potential of the black body emission, which is this point. Because there's no flow of heat through this surface, all of this area of the surface, we just assume that it's not even there. Much the same way that we did for black body, except that here we don't have any heat transfer through the surface. For black body, you do have heat transfer through the surface, so your radiosity is equal to your black body emission, and also there could be heat transfer to your black body. But then in this case, there is no heat transfer. The same way that when you do have an electrical circuit and part of the circuit there's no current in that part of the circuit, we don't really consider that part of the circuit because there's no current. Even if there was any resistance, we basically remove everything in our calculations because there is no current. Here we do the same thing. Because there's no current of heat in this re-radiating surface, then we assume that that area is not even there, and then we call our radiosity equal to our potential for the emission of the black body. The rest of the surfaces, this is just an example. This example specifically is for 3-surface enclosure with a re-radiating surface. One of the surfaces is re-radiating. If you take a look at the picture, the top surface has the subscript R, that is our re-radiating surface, and then you have surface 1 and surface 2 as well. So then your circuit looks much like what is drawn here, and if I were to actually figure out what would be the heat transfer from, let's say, surface 1 to surface 2 through radiation, I'd be able to do what I have always done for circuit analysis. Back in conduction analysis, you can analyze circuits using the same rules that you used in the electrical circuits. Here the same way. The resistances are different, the nodes are defined differently, but the analysis of the circuit would be the same. So then I'll be able to say, if I want to calculate, for example, the amount of heat that goes from surface 1 to surface 2, I'll be able to say that I can start from this node EB1 and go to node EB2, and that's what I have written on the top of this relation, Stefan-Boltzmann constant, T1 to the power 4 minus T2 to the power 4. And then I'll divide that with whatever resistance exists in between these. Now, all the resistances here, if you take a look, it doesn't look quite like the parallel heat flow that you've seen before, but if you actually rewrite it, I can draw the circuit a little bit differently, and you'll see that it will actually look more like a parallel heat transfer flow in parts. So for example, your node 1 would be, your EB1 is here, after EB1, I have one resistance, which is this resistance here. I'm not going to name it here because it will make it very looking very messy. I'll just put the nodes there. Then I get to node J1, and then after J1, I'll have another resistance, which is this resistance here. Then I get to J2, and then I get to the resistance on the surface of my surface 2, which is this resistance, and then I get to my EB2. But then that's not all. I also have two other resistances. Although this is a re-radiating surface and no heat passes through it, there is heat that arrives on the surface and gets re-radiated back to the other surfaces. So I still have to look at this path or this resistance and this other resistance here. So those, I'll take a look to see that the left path starts from J1. So I'm going to say that that's from J1. And then I go and I'll have a resistance. And then I get to point JR. And then I'll have another resistance only to go back to J2. So this is how the circuit now looks like. This is exactly the same circuit that you have on the right hand side. You could draw it like this. I mean, I could make it look a little bit nicer, more like what a parallel circuit looks like. Let's just draw this part again. So if I have my J2 here, then my EB2, this goes exactly like a parallel heat transfer flow. So then, in order to analyze the circuit, I'll write EB1 minus EB2, and then I'll divide this by all the resistances that are in between, and in order for me to calculate a net resistance, or an overall resistance, I'll be able to say that the middle ones, this one here, and this one here. The top two ones are in series, so I'll add them up, and that's how I've added up those two. But then they are in a parallel relationship with the one in the star one in the lower case, which is how I'm going to then deal with this A1, F12. If you actually write this, you'll be able to see that this middle term is taking care of all the three resistances in the middle. And then the side one on the left and the side one on the right, this is the one with 1 minus epsilon 1 divided by A1 epsilon 1, and that's the one that shows up here. I'll just add it to the middle resistance because it's in series. And then on the right hand side, I have the same. I add the right hand side. So it's as if I have three resistances that appear in series, so I'll add them up. So that's why you have three terms in the denominator. But then the middle term is actually like there's more to it. You do have two resistances that are in series together, but then in parallel with another one, and that's why you have this relation. I do encourage you to see if you can derive this yourself. You're not supposed to always derive these types of relations, but it does help a lot. You can't really, there's so many different configurations of these circuits, and unless you learn how to write a relation like this, you will never be sure that for your problem, there's a relation that you can go to the book and actually use. So I strongly encourage you to pause the video here and see if you can actually arrive at the relation that I have given you here on the bottom in the denominator. So that middle term, see if you can actually write the three resistances in this way. Now here I'm going to derive what I asked you to derive in the previous slide. The three resistances that I want to deal with first are the 1 over A1 F1R, 1 over A2 F2R, and in the denominator, in the bottom one, I'll have 1 over A1 F12. I'll first take care of the top two ones. I'm going to call them 1 and 2, or in other words, in this picture, they'd be 1 and 2, this one. So these two, I'll call them the net, or the total R, or resistance. I'll call it R12. So R12, because they're in series, I just add them up. So that will be 1 over A1 F1R plus 1 over A2 F2R. Now I have 1 R12, and I'll have to look at it, so now my circuit becomes more like this. That's my EB2. This is my EB1. This is my J1. This is my J2. This is still my 1 over A1F12. I haven't touched that yet. But then for this part, I've basically broken it down to R12. Now I have R12 and I have 1 over A1F12 that I have to find one overall resistance for it. So I'm going to call the bottom one 3. And then I'm going to calculate R123, which is basically the overall for these three resistances. So I'm going to say that R1 over, well, I'm going to start with saying 1 over R123. 1 over R123, the relation for parallel resistances was 1 R12 plus 1 over R3. This is the relation for parallel resistances. Now I'll substitute the R12 and R3 in this to see what I get for 1 over R123. So I'll get 1 over R123, which is going to be 1 over A1 F1R plus 1 over A2 F2R. I could just write the denominator and make it to the power negative 1, but I'll do that in the next step. Plus 1 over R3 is 1 over A1 F12, which is, I can just bring it up and I'll say A1 F12. Next step is to make everything to the power negative 1, and the reason for that is this 1 over R123 is sitting in the denominator. I want to bring it up. So I'll say R123 is equal to everything on the other side to the negative 1. So, or I'll just keep them in the denominator if I want to. I'll say that this is all 1 over all of what I have, which is 1 over A1 F1R plus 1 over A2 F2R, and then that's all plus A1 F12, all of that to the power negative 1. Now this is what I have for my R123. I'll add this to the other two resistances on the two sides. Let's call those 4 and 5, or here maybe 4 and 5 here. And that should give you the denominator here. This is your 4, this is your 5, and the middle term is your R123, which is, you can simplify this a little bit to look more like what you have in the middle here, but it's all the same. The reason I don't write it as like 1 divided by this, instead of writing 1 divided by this term, I've actually used this negative 1 power. So that's 1 divided by all that you see inside of this bracket. So if you actually take a look, I have my A1 F12, which is here, and I have 1 over all those terms, which is this negative 1 power here. So then I'll have 1 over A1 F1R plus 1 over A2 F2R. Something that sometimes we want to do is to calculate the reradiating surface temperature. And that's quite easy to calculate because your reradiating surface, you can write around the node JR, around this node, you can write the energy balance or the flows of radiation. So I can say that on the one side here, I have QR equal to 0, so there's 0 Q here, and whatever arrives from this side should be equal to whatever leaves that node. So in other words, I'll be able to say that whatever arrives on the left side, which is the balance between J1 node and JR node, and then the balance between JR node and J2 node. So in other words, I can say J1 minus JR divided by my resistance in between them is equal to JR minus J2 node, again, resistance in between them. And then, of course, JR node, I know that it's equal to the emission, the black body emission potential, and I put the Stefan-Boltzmann constant and T to the power 4 instead of my JR values. And there, I got it. I have a temperature of the reradiating surface showing up in my relations. If you have all the other factors, like for example, if you know your JR and J2 and Stefan-Boltzmann constant is a constant that we know, and if you have your area 1 and 2 and your view factors, then you'll be able to actually calculate your reradiating surface temperature. Do we always have these values? No, but as you have seen in the examples before, there are ways for us to write the balance in the other nodes as well. For example, in node J1 and J2, you could write balances to figure out what those J1 and J2 are. View factors are totally geometrical features of what the setting that you have, so that is separately calculated. So there are ways for you to calculate those other terms, and then once you get those, you'll substitute them in this relation to calculate the temperature of your reradiating surface if that's what you're interested to get.